Bohr model, you have your nucleus, your protons, your electrons. Outside of that, your first bubble holds 2. Then you have 8. Then you have Bohr thought up to 18. Remember drawing those in middle school? Yeah, physical science. Okay, so that's magnesium. The address that we drew when we did electron configuration is called ground state. It's what we know. Okay? It's what we did the other day when we did the arrows, all that stuff. We go with that. Okay, can we go back over how I got that? Can I go back over it? Or no? Okay. So it's got 12 electrons. I know that because that adds up to 12. The S and the P tells me where I'm at in terms of block. The 1, the 2, the 3 are called the energy levels. That's typically the row I'm on. Remember, your rows get weird when you're talking about the D block because they're one below the party. Because if the D block was really where it was supposed to be, it would be pushed out way over here. Okay? Out to this side. Now, so electrons are at the ground state. That's how they are when they're just normal. Now, magnesium is a metal. I've got magnesium metal sitting in a cabinet in the back. It's just sitting there. You have aluminum sitting in your house in foil state, right? You use it all the time. You wrap food in it. You bake with it. Line cookie sheet, protect your grill, whatever. You use it all the time. It's not reactive when it's in ground state. But what happens, I'm going to use y'all or your younger sibling or cousin or whoever, if you give them some caffeine, some sugar, something that gives them energy, what happens to them? They go nuts, right? They get excited. Electrons do the same thing. They get excited. They go up to what's called excited state. But what electrons do you think can move? Which ones can move? The valence. Which ones are the valence in this case? The 2, right? The ones way out here. So the valence electrons move. They go up to what's called excited state. When they go up to excited state, they do that through heat or some form of energy, electricity, maybe a high-intensity light stream, something like that. Now, when they go up in energy through light, through heat, whatever, they get excited. But they can't stay there. Can you stay excited very long? No. Even if you're at the best party ever, eventually, you got to go home. It's curfew. Eventually, you can't ride the best roller coaster at Disney World, Six Flags, not very far, wherever, that many times. You can't eat enough sugar, drink enough Red Bull, Monster, whatever your favorite, vice of choice is, and not have headache the next day, or whatever. You're going to crash. So, same thing happens to the electrons. So they're going to absorb energy, they're going to raise energy levels, but then they'll go in excited state, but then they fall back to ground state where they want to be. When they fall back to ground state, they emit light. Now, when that happens, because it happens so quickly, we see it as a color transition of light. Anybody know what the speed of light is? Give that physics test. Okay. The speed of light is 3 times 10 to the 8 meters per second. It's why you will see a flash of light, like from the tip of a gun, if you're close to it, before you hear the sound. Right? Because the speed of sound is 340 meters per second. Okay? So you'll see it before you hear it. It's why they say when there is a bad storm, you'll see the lightning before you hear the thunder, and you can count 1, 1,000, 2, 1,000, 3, 1,000 to determine how many miles away it is. You know that? No. Why do you do that? major classifications, metal and non-metal. You're going to have to figure out how based on your data table. Emits a certain color based on how high it falls. Remember the colors of the rainbow. Colors of the rainbow are red, orange, yellow, green, blue, violet, right? So based on how far it goes up and how far it comes down, this is how much color you're going to see. How excited it gets. How much room it has to move through. Okay? Make sense? Notice I like the story time. Don't like to just can't do it. And be that teacher from the peanuts. The board thing. This is my friend Michelle. Michelle is up at KSU, taking both of my classes, honors and weekend. So she's acting as our TA today to hang out with us and stuff like that. Well, that's great. So she's probably going to start some video real fast. But she's also going to help us light our bunker burners and all that stuff. So you're going to see different colors. You need to kind of analyze your lab table, or your data table for a minute, figure out what toxic is. In your data table, second here's barrel here before the end of the bell. And if you need to figure out your warning colors, okay? You're going to figure out the compound name. In the fourth column, you're going to give me the part of the compound in regular state, the way we regularly write it. Now, look at the compound. We haven't talked anything about compounds yet. We've only been talking about elements, right, and atoms. What do you notice, not knowing their names at all, but just looking at the column, or what's in your column, do you think it's the first half of the compound or the second half of the compound if you were to give it a first name and a last name? That's possibly going to make the color. Looking at all the different things I gave you in that list. The first half or the second half. Looking at all the different choices I gave you. Why do you think it's the first half? Because there's a lot of different ones of those, right? Whereas there's a lot of things that say NO3 even though there's different numbers. And a lot of things that say CL even though there's different numbers. So the back half of a compound, its last name, when they're ionic compounds, when it's metals and non-metals, does not go up and down in energy level because it's accepting that electron that moves. The metal on the front half does. So you're looking at the transition in the metal. So in that fourth column, I want the original electron configuration, 1s2, 2s2, for whatever the metal is, the first part, before you get to NO3 or Cl2. Okay? In the next column, in the last column, I want what it is in its ionized state. Remember how on the back of your periodic table, we wrote if its oxidation number, it loses this many electrons? So here's what I mean. Let me give you an example. Okay? We said this. I'm going to give you two. What if we have something like this? If we have MgCl2, and then we have something like, I don't know, Cu, NO, two. All right. Now, I picked Mg because it's in one of my tall columns. It's in one of the first two tall columns. Do I know, because it's in one of the first two tall columns, what this thing's oxidation number is? Yes, 2 what? Plus or minus? 2 plus. Good job. So, Mg on its own, we said on the last page, was 1s2, 2s2, 2p6, 3s2, right? Now, if I want Mg2 plus, okay, what does that 2 plus mean? mean? Does it mean I take off 2 or I add 2? I take them off. Because it means it has to have an overall positive charge of 2. Okay? So if I need to take off 2, I need to take off the last 2 electrons, which happens to be 3s2. Okay? Now, the Mg, I'm just going to take it off. I'm just going to say 1s2, 2s2, 2p, 6. All right? Now, I also gave you the other day an ion chart, right? I told you with the transition metals, iron, copper, cobalt, nickel, things in the middle flat part, you had to know what they were hooked to, right? To figure out their charge. Okay, here's how you do it. A compound has to have a total of 0, right? Can't be positive, can't be negative. Here's what you do. So I'm going to say x plus 2 times something equals 0, right? That's just a number. If I look on my chart that looks like this, on the back, it tells me that NO3, in this little box over here, is in this -1 box. Okay? That -1 is what goes in this box right here. So x plus a -2, that looks really pathetic, Teddy. Equals 0. Okay? So what's x? Positive or negative? Positive, because let's bring it over. X equals plus 2. That's Cu in its oxidative state. Okay? So, you're going to have to use your ion chart. Does that make sense? Can we do another one?
Yes, please.
Yeah. Okay. So, let's try this one. I'm just going to make something up. It's not on your sheet. Okay? Mn Cl, because we're only using Cl's and NO3s, right? So I'm going to show you the same thing. That's equal 0. X plus 4 times, we know the charge of Cl, right? It's on my column, it's halogen. But I can also look back here and look at fluoride, Cl -1. Cl's in this -1 column, I'm going to say -1. 4 times -1 equals 0. X plus -4 equals 0. X equals plus 4. This is the charge of Mn in oxidized state. So on my chart, I would write Mn is 1s2, 2s2, 2p6, 3s2, 3p6. What's the number for Mn? 4s2. How many is Mn? Where's Mn? 25, so I need 3d5. 3d5. But then if I need a plus 4, right, I'm going to take 4 out of the 5. So I'm going to go Mn plus 4 is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Oh, that looks even more board. Is that a word? 3, 1. Okay? And that's how you figure out the charge of a transition metal. You just set it equal to 0. All right. Now, that's how you fill out your data table. I'm creating a PowerPoint right now, so that's 3 questions that you're going to do after you fill out your data table after the lab. The first you got to do is the lab stuff. Let's get that.
If you're looking at the MN form, how do you tell between that and what would be like
Regular MN?
or no titanium? Because would that have or whatever would be the last have the 3D one?
Have the 3D one?
Yeah, like
Because 3D one would be SC, right? Because it's 21 electrons.
yeah.
Okay. Good question. So SC is 21 electrons, and so is Mn4 plus. Is 21 electrons. Those are what's called iso electronic. I can't spell. All that means is that they have the same number of electrons. Because like isosceles for triangle, meaning they have the same length and same angle, right? All isoelectronic means is they have the same number of electrons. So if all I gave you was the number of electrons to write the configuration, you could give me a bunch of possible answers. But if it's in a compound, it has to be whatever it is. Okay? Now, I could give you, in a multiple choice question, I could say, I could give you pairs of elements and say which 2 are isoelectronic, and you have to.
You'd never just give us the electron configuration.
God, no, because there's like 8 quadrillion, unless it's obvious, and say, in the ground state form, what is this? I would have to be very, very intentional and specific. Okay? Great question. All right, here's what's going to happen now. I kind of went through the lab. We're going to go through it one more time with that. When you get over here, you're going to, each table has a striker. We've been soaking some Q-tips. Okay? Right now, the Bunsen burners are off. The burner is the jet on thing. It's pointed toward either the window or the bulletin board. You're going to turn it where it's even with the center of the 2. You're going to strike it fairly fast, like this, putting also some counter pressure on what I call the back of the hat, so that there's good contact with the flame. Okay? You're going to strike it, it'll turn on. Then, you're going to come over here. Each of my 14 or so samples are nice and labeled with the compound formula on it. All that's moving over here is you with the Q-tip. And remembering which one you have. Do not bring the jar over. Okay? Because we're going to rotate through. There's 5 different tables set up. There's about 30-ish of you. That means 6-ish at a table. You need a lab apron. You notice at the beginning of the semester, I didn't go over lab safety. Well, it's important that I don't do it unless we do it at the right time. This is the back. This is the front. Over your head like a cooking apron. You can tie it, not tie it. Today is not one of those days where I'm going to say tie it because you have to tie it. Because, well, we're not using liquid acids all the time. Goggles are in here. You have to wear a pair. Your hair needs to be, ladies, I don't know, fairly long. It needs to be either twisted back or something like that. If you have a jacket on, please take it off so that when you go like this, you're not setting your arm on fire with your sleeves. Okay? You're going to go through the 15 samples, watercolor. Since it is a gas flame, you know how if you use a gas stove or whatever, it'll have the 2 blue cones. The outer one is not as hot as the inner one. You want your little Q-tip that's been soaking is to enter that cone. It'll show a color. Sometimes it is somewhat blue, sometimes it's orange. But if you get a color that's not orange, and then you get orange, guess what you're doing? You're burning the Q-tip. Don't burn the Q-tip. There's like 38 sprinklers in this room. I'd like to keep my job. It is Friday. And right now, because payday's not till the end of the month, there's seriously $8 in my checking account. That even like that. So, let's get stuff. Let's get done. This is a fun one. Here's the whole thing. We're gonna cut door. You probably want your phone. This is good one to snap videos, Instagram story, all that stuff. Okay? Let's